Okay, today we are looking at tutorial 6, question 24, which is about gradients and Hessians. Consider a function f, which is a function of the vector x. The gradient is its first derivative, and the Hessian is its second derivative. Part A is let the vector x equal x comma y, where they are both real numbers, with x and y being greater than or equal to 0. And the function is equal to square root the vector x dotted with the vector x all to the power of a. We are told to calculate the gradient and the Hessian if a is equal to 1. So if we make a start, our function becomes just square root the vector x multiplied by the vector x when a is equal to 1. If we now use the information that the vector x is just xy, we get xy dotted with xy, which gives us x squared plus y squared all to the power of a half. Now, to work out the gradient, where the gradient is just the first derivatives, when we differentiate our function with respect to x, we get x squared plus y squared all to the power of minus a half. That is simply because to differentiate this we use chain rule, so we times by the power, subtract 1 from the power, and differentiate the bracket, and so we get this, and this is the same as this. And then we need to find partial derivative with respect to y, and that is simply going to be y brackets x squared plus y squared to the power of minus a half. Cool. Now, to work out the Hessian, we must work out the second derivatives, so that would be these. So when we differentiate this with respect to x, again, we will get x squared plus y squared to the power of minus half. So that's just me doing this by product rule, just differentiating the x first. And then I will get minus x squared plus y squared to the power of minus 3 over 2. And that is just because when I differentiate this part, the x stays the same. I will have to drop down the power, rewrite the bracket, minus 1 from the power, then multiply by the derivative of the bracket, which is just 2x. So that and that cancel, and we're left behind with x times x, which is x squared, and then x squared plus y squared to the power of minus 3 over 2. Now, differentiating it with respect to y, we just get minus xy bracket x squared plus y squared to the power of 3 over 2, and that is the exact same over here. And now differentiating this with respect to y, I get x squared plus y squared minus a half. Again, doing this by product rule. When I differentiate y, that's what's left behind. And then I'll get minus y squared, x squared plus y squared, power minus 3 over 2. Now, I am going to make x squared plus y squared to the power of 3 over 2 the common denominator for all of these. So when I do that, I need to multiply this one by x squared plus y squared, and this one just stays the same, so we just get minus x squared. And over here, we just get minus xy and x squared plus y squared to the power of 3 over 2 underneath. Same thing over here. Over here, to make x squared plus y squared power of 3 over 2 the same, the common denominator, we need to times this first part by x squared plus y squared, and the minus y squared stays the same. So we get this. So the x squareds cancel over here, and the y squareds cancel over here, and we're left behind with y squared over x squared plus y squared to the power of 3 over 2, minus xy, x squared plus y squared to the power of 3 over 2, and minus xy, x squared plus y squared to the power of 3 over 2, and x squared plus y squared to the power of 3 over 2. Now, if I take 1 over x squared plus y squared to the power of 3 over 2 outside of the matrix, we're just left behind with y squared minus xy, minus xy, and x squared. So this would be our Hessian, fully simplified. Now, so that's part A done. If we look at part B, find the eigenvalues of the Hessian for arbitrary values of A not being equal to 0. Cool. So in order to do this, I'm going to rewrite the function, but this time we have the function to the power of A, which we can write as x squared plus y squared all to the power of A minus divided by 2, or A over 2. So if we work out the gradient for this function, we get A over 2 x squared plus y squared, A over 2 minus 1 multiplied by 2x, and A over 2 x squared plus y squared, A over 2 minus 1 multiplied by 2y. And this we can rewrite as ax x squared plus y squared, a minus 2 over 2, and then ay x squared plus y squared, a over 2 over 2. We will find the second derivatives of these two expressions. So differentiating this with respect to x gives us a x squared plus y squared to the power of a minus 2 over 2 plus ax brackets a minus 2 over 2. So that's me times in by the power, and in brackets x squared plus y squared minus 1 from the power will give us a minus 4 divided by 2 multiplied by the derivative of the bracket, which is just 2x. Now if I differentiate this with respect to y partially, we get ax a minus 2 over 2 x squared plus y squared, a minus 4 over 2 multiplied by 2y. And that is the same over here. So not quite the same, as these two have just swapped places, but when we simplify it, it will be the same thing. And finally, differentiating this with respect to y will gives us this. Cool. If we now begin to simplify this, what I will do is factorize out x squared plus y squared to the power of a minus 4 over 2. What that will leave behind is x squared plus y squared over here, and over here it just leaves behind a minus 2 x squared, because that 2 and that 2 cancel out. Cool, hopefully you can see that. Over here, if we take out the same thing, we are left behind with a minus 2 xy, and that's going to be the exact same over here. And over here, when we take out x squared plus y squared to the power of a minus 4 over 2, we're left behind with x squared plus y squared, and then plus a minus 2y. Now, taking out a x squared plus y squared to the power of a minus 4 outside of the matrix, we are left behind with x squared plus y squared plus ax squared minus 2x squared, a minus 2 brackets xy, and then a minus 2xy, and then and then x squared plus y squared plus ay minus 2y. Cool. And then finally, we can write this matrix as ax squared plus y squared minus x squared, a minus 2xy, a minus 2xy, and then ay squared plus x squared minus y squared. Cool. So to work out the eigenvalues of this 2 by 2 matrix, I'll just use the characteristic equation, which is y squared minus the trace of this matrix, which I'll call A, multiplied by lambda plus the depth of this matrix A. So we get y squared minus ax squared plus ay squared. So the trace of a matrix is just what we get when we sum the leading diagonal. So when we sum these two together, we just get ax squared plus ay squared. And then if we work out the determinant of this matrix, we will have to do ax squared plus y squared minus x squared multiplied by ay squared plus x squared minus y squared subtracted from a squared minus 4a plus 4 brackets x squared y squared. So that's just me multiplying these two. Okay, expanding these two brackets out, we get this. Now, if I expand this out, we get minus a squared x squared y squared plus 4a x squared y squared minus 4x squared y squared. So this and this cancel out. And if we collect like terms, we're left behind with this. Now we can factorize a out. So we're left with this, and this should be y to the power 4. And then if we just factorize out the negative sign from here, we are left with x to the power 4 plus 2x squared y squared plus y to the power 4. So now this can be factorized into x squared plus y squared all to the power of 2, and this can be factorized into x squared plus y squared all to the power of 2. So now if we factorize out x squared plus y squared all to the power of 2, we're just left behind with a minus 1. So that is our determinant. So we have a minus 1 x squared plus y squared is all equal to 0. If we now use quadratic formula to solve this quadratic, we get a x squared plus y squared plus or minus square root a squared x squared plus y squared all squared minus 4ac, so 4a minus 1 x squared plus y squared all over 2a, so just 2. If we now, just looking inside the square root, factorize out x squared plus y squared to the power of 2, we're left behind with a squared over here, and over here we're left behind with minus 4a plus 4 if I expand this out, and that's all divided by 2. Now we can factorize the quadratic a squared minus 4a plus 4. It is just a minus 2 all squared. All of this divided by 2. And so we are left with, when we square root, x squared plus y squared and a minus 2 all divided by 2. Now I'm going to factorize out the x squared plus y squared all over 2, and we will be left with a plus or minus a minus 2. So our two eigenvalues are x squared plus y squared all over 2, and then a plus a minus 2. And our second eigenvalue will be x squared plus y squared divided by 2, brackets a minus a plus 2. So this eigenvalue just becomes x squared plus y squared, and this eigenvalue becomes a minus 1 x squared plus y squared, as this is 2a minus 2, and if we divide it by this 2, we're just left with a minus 1. This isn't quite our eigenvalues for this matrix, as we still need to times it by this, because we've taken this out of the matrix. So if we go ahead and do that, our eigenvalue of the Hessian now will be a bracket x squared plus y squared to the power of a minus 4 divided by 2, a minus 1 x squared plus y squared. And if we do the same for this second eigenvalue, we will get a x squared plus y squared a to the power of a minus 2 over 2. Hopefully you can see why that is. That is just me doing this times by x squared plus y squared a minus 4 to the power of 2. Cool. If we just rewrite this in a neater way, we will get a minus 1 x squared plus y squared. This multiplied by this will just be a minus 2 over 2. Cool. So here are our two eigenvalues. Hopefully that made sense. Cool, so that's part B done. Part C, for which values of A is the Hessian strictly a positive definite? Cool, so for part C, when a Hessian is strictly a positive definite, the eigenvalues are positive. Therefore, we are going to look at our two eigenvalues and we're going to make sure that they are greater than 0. Cool. So one thing that we do know is A is greater than 0. So if we look at this, A is going to be positive, and then any number squared plus another number squared is going to be positive. And then a positive number to the power of any number is also positive. So we know this is also positive. So this is all good. If we look at this now, from before we know that this is positive. So essentially, we need to solve for a brackets a minus 1 being greater than 0. So if we solve this as a quadratic, we get 2 roots. A is equal to 1, a is equal to 0. Because it's greater than 0, we're going to have a greater than 1, or a should be less than 0. As we already know that a is greater than 0, we don't need this condition, so not needed. And so we can just say, therefore, a must be greater than 1 for the Hessian to be strictly positive, because we know a is positive, and this is always going to be positive when a is greater than 1. So there we go, and that is part C done. Hopefully that made sense.